suffered enough. So let's do some cool stuff. So what I'm going to go and get started today is go over some questions that'll allow us to get the first section done, and we're going to get started on the second section today, I hope. So the first question, the first kind of questions are going to be partial derivative, and the second group of questions are weird ones that look like this, and the last one is actually Laplace, because we missed him. So already had a request for a question that looked like that. I've just invented my own version of it, but it's essentially you've been asked to find the partial derivative dz by dx when the information is given in this format. And whenever you see information of a function where z, which is the primary variable here, is mixed up with all the others, then it's implicit. And I hope I've left enough room there. I may not have. So maybe I should do it here. So e to the power of 2z is x squared z plus y cubed. And we are going to go and find the partial derivative of z with respect to x. Okay. So you take each piece and you differentiate it, partial derivative with respect to x. So z's a little bit different than y cubed, for instance, because z is part of this. So if you differentiate e to the 2z, you will get e to the 2z, agreed? But it's a little baby chain rule. Don't you also have to differentiate the 2z? Now, in good old Calc 1 world, that would be just times 2. Unless you were doing implicit, then it would be times 2 dz by dx, and that's what's happening here. It's just a partial dz by dx, but it's very like Calc 1, right? You know, y cubed gets you 3y squared dy by dx, that kind of thing. Now, this fella here and this fella here. Let's do the guy at the end because he's easy. Right? If you differentiate this with respect to x, you get this. This guy here is a problem. The answer is not 2xz, because x and z are both considered variables in terms of x. So that means that I'm going to have to do a little product rule. So I'm going to think of it as x squared times another function of x that just happens to be in z in this case. So when we look at it from that perspective, it's going to be f dash g plus f of g dashed. I'm just rearranging this a tiny bit. There's nothing really major going on here. Right, f dashed, differentiate partial derivative with respect to x. You get 2x, leave the other guy alone, plus first guy untouched, and you differentiate the second guy with respect to x. In this case, not a lot happens, because if you do z with respect to x, you get that guy. Now, we are after dz by dx. Right now, we've got an expression where the thing that we need is in two separate locations. So all I'm going to do right now is algebraically solve for dz by dx. So I've got to get these guys together. And I think the best way for me to do that is to subtract this guy here from both sides. So I'm going to subtract an x squared dz by dx. So that's like the first phase. What do you think I'm now going to do to the left-hand side that'll get me closer to finding dz by dx?
Factor out dz dx.
Right?
dz dx.
Yeah, I knew what you meant, yeah. So this fella. And then I hope by this point in time you realize that all you need to do is divide. Right, does that seem, does that process seem reasonable to you? Right. Okay, so That is the first one of the two. The second one of the two is a guy that looks something like this. And we're given a relationship with my vague knowledge isn't that the formula for the total resistance when the resistors are in parallel, I think. Parallel? Hey, it's a formula.
So.
I believe so.
Right. So, not that that matters one bit for our question, because as far as we're concerned, it's math, right? And I don't really, me personally, I don't care what the equations are or even where they come from. On the other hand, a lot of people who are using math as a tool rather than, you know, the thing itself, really do like to know what these formulas do.
I think the
Right,
one
in
in
this
web
case,
design had 3 things on the right.
yeah, I've
Made it
just
more
taken off one of them to make my life a little bit easier as well. It really doesn't change the answer that much, to be honest. All right, so we're being asked to say find this one. So the partial derivative of capital R with respect to the variable R1. So it is implicit because basically that doesn't say R equals, that says 1 over R equals, right? So it is a formula. And if you think about that, isn't that the same thing as R to the power of negative 1? R1 to the negative 1 and R2 to the negative 1. So these are equivalent. This format, although it looks ugly, is actually a better format if you want to differentiate, because it's obvious that we're going to just use power rules, right? Or maybe it isn't. But it should be obvious, right, that we're going to use a power rule. Right. Differentiate. This fella, you multiply by the power, you reduce the power by 1, and because capital R is being considered a function of R1, you finish with that. It's just like, you know, y cubed gets you 3y squared, but you always finish with the dy by dx. That's the implicit thing happening here. Now, this fella here is simply just multiplied by the power, reduce the power by 1. That's what you get if you differentiate R1, this 1 over R1 with respect to R1. What do you get if you differentiate 1 over R2 with respect to R1?
0.
0.
0, so I won't even bother writing it. My next line is only me trying to make it easier to see what the heck the answer looks like. Negative powers are not very easy to, you know, to see, right? Wouldn't it make much more sense to convert them back into the fractional versions? All I need to do now is isolate that guy, because that's what we've been asked to find. Okay, how would I get from here to here? What should I do to both sides?
Multiply both sides by negative 1 over R squared.
And if you multiply both sides by negative, is it 1 over R squared or R squared?
R squared, sorry.
All right. And if you do that, the two negatives cancel, and you get that. That's all we need to be able to do. But I'm going to, because I know quite a few of your engineers or may choose in the day. What we have here are some resistors called R1 and R2. That's 5 ohms resistor, that's a 20 ohms resistor, whatever it is. But can you imagine a situation where this is a circuit board where these are allowed to vary, right? You have a little dial, you can change the resistance on each of them. And the guy that you're calling R is the total resistance between the start and the finish of the circuit. So what's this saying? It's saying the rate at which the total resistance is changing if you only vary the R1 resistor is, right, so how much it's increasing or decreasing, is whatever the total resistance is squared divided by what the resistance on R1 is squared. So I guess in physics you would say the rate of change of the total resistance with respect to R1 is directly proportional to the resistance squared and inversely proportional to the circuit R1 squared. And two of you probably nodded at what I just said and the rest zoned out, but that's fine. You only need to do that, right? That's your job. What it means, how you use it, that's for those people who need to know, right?
Cool.
Are we cool? Right. I think I'm going to share with, sorry,
Can I see the work to the bottom paper there?
this one here.
No, the other one you did before that one.
Oh, this one here. That was the other one.
Yeah.
I'll keep that there for a minute then. And this is a video, so you can always go to tomorrow and look at it if you want to. So you have to frantically write down every step of the working, which is probably a bit of a bind if you're trying
I
to
took a
listen at the
picture
same.
of it, so you're
Right,
good.
we're good. Okay. So, well, I was going to share with you. Depends who you get Calc 4 for. If you want people who are really into applications, then Karen Hasselbach is got a really good foundation in that. She knows all sorts of cool applications to what various calc things do. A couple of the others as well. But don't ask me, because half the time I don't care. For me, the best math is actually the math that nobody finds any use for. I just think math for its own right is kind of cool. And so I don't really spend a lot of time being too concerned about, oh, why should I find partial derivatives? I think they're just cool. They're kind of fun. Right, second kind of question looks like this. This is a homework type of question. You're given some function of z, and it's not given in the usual format. It'll be given in terms of two functions or a single function mucked about with. Here are some other examples of what that looks like. Z is some function f of x times some function g of y. It's trying to generalize particular combinations of functions that you might get. For instance, you know how sometimes you get a z equals x cubed sine y? Wouldn't that belong to that family? Or you might get sine x over y cubed. That would be this family. You might get sine x take away y cubed. That would be this family. This would be a function where you might have, I don't know, x plus y brackets all squared, or the cosine of x plus y, right? That's what this would be a family member of. And this one here would be a function where y over x was present. So can you imagine the cosine of y over x, things like that. And what we're going to do here is find, and just because I want to, let's just find that guy in each case. Now, you may say, well, what's my answer going to look like? Because I don't know who f of x is. I don't know who g of y is. That's fine. Your answer won't have a specific value. It will be general as well. So I think I'll go red on this. Let's look at this one. F of x times g of y, right? If you differentiate this partial derivative with respect to x, don't you just get whatever the derivative of that is times g of y? So one liner. Now what about this fella? F of x over g of y. Right. Isn't g of y a constant? So it's really just not going to have much to do with this story. Can you see that all you're going to get is f dashed of x over g of y? What do you think you're going to get out of this one if you find dz by dx?
F prime of x.
Yeah. Americans use f prime. You know the correct word is f dashed, don't you? What's the other one I use a lot? I'm not going to change now. I've been teaching with those words for too long. I say brackets a lot. You know, when I say brackets, I mean those things. What do you call them again?
Parentheses.
Have you just got used to me when I say things, you know what it is, because it's maybe not the word you use, and after a while you don't even know that I'm using it? I hope that's what happens. So when I
Yeah.
say f dashed of x, are you just saying I means f prime, no biggie?
Yeah, they're just
Right.
interchangeable. I just don't say F dashed.
Well, you should. It's a much nicer way of saying it. But what do I know? I mean, what does prime mean? It doesn't mean anything. Isn't dash a little stroke? Huh? What do I know? Oh, this one might get you thinking. F of x add y. Partial derivative with respect to x. Last few seconds. It's almost not an answer at all. It's just f dashed of x add y. Now this one is sneaky. The last one, obviously the last one should be sneaky. If you differentiate this with partial derivative with respect to x, you will get that guy. But there is a difference. Technically, in this question, it's times the derivative of x add y, which is times 1. That's why you don't bother about it. But in this case, isn't that y over x has to be differentiated with respect to x? And if you do y over x and you differentiate it, you will get negative y over x squared eventually. You imagine y times x minus 1, whatever way you do it, but that's what it becomes. So this one here gets you that guy. So most of those z is a function of, you know, x and y. Most of them are one-liners and pretty basic, but they're going to chuck in a couple of weird ones like this last one is pretty weird. Are we okay with this type of question now, how you would find dz by dx? You could also be asked to find dz by dy. Wouldn't it be very similar answers? There wouldn't be a much difference. And now we're going to do Laplace. This is Laplace's equation. It says that, well, basically the assumption that u is some function of x and y, right? The second derivative of u with respect to x plus the second derivative of u with respect to y is equal to 0. If you have a function u, right, a function of x and y called u, that has this property, then it is a solution to Laplace's equation. This is Laplace's equation. And what you're being given in the homework is some examples, and you have to check, does it work or not? Is it a solution? So essentially what you're going to do is find second derivative with x, second derivative with respect to y. You're going to add them together. If the answer is 0, you say, yes, that is a solution to Laplace. And if I remember right, the homework is little dots outside, and you pick it if it's right and you leave it blank if it's not. Okay, so you got the gist of it. For those people who like to know what that guy is, before the class started, I thought, well, I should at least try and make things relevant to the engineers amongst us. Laplace's equation is, or solutions to Laplace equation are used in heat flow. So if you're looking at a spherical object in the shell of it, how would heat move around that surface? Evidently, it gets used by that. I also believe, but don't quote me on this because I didn't read this, but I think I remember reading it somewhere, that Laplace's equations also get used in solutions to wave problems, where you're trying to figure out a wave that has certain properties. So here are 3 examples. I'm going to pick the first one and we'll check it out. So, first partial derivative with respect to x, second partial derivative with respect to x. First partial derivative with respect to y, second partial derivative with respect to y. Would you agree in this particular question, it works? So x squared minus y squared is one of the many, there's an infinite number, solutions to Laplace. Okay, now, to save time, I'm now going to do that guy. I guess I'll change to green. For this guy, won't the only difference be both of them are plus? 2x2, 2y2, right? Plus, whoops, plus. But when you add those two together, do you see you get the answer 4? So that one does not work. And so you'll leave that one blank. Oops, that one does not work, right? I'm about to do the last one. It's pretty messy looking. And it is e to the negative x cosine y, take away e to the negative y cosine x. And I guess the question is, do you think this one is going to solve Laplace's equation? What's your gut feeling, yes or no?
Yes.
Any particular reason, or it was just a gut feeling?
Just going with a gut.
Yeah, why not? It's, well, I wouldn't give it away, but it's a good choice.
I mean,
So,
your first term and your second term are the exact same and you're subtracting them. So
yeah, the logic looks like the math would probably end up with two things that are plus and minus and they cancel out, that kind of thinking. Yeah, I would agree. That seems reasonable. Okay, so we'll start with this fella. If you do a partial derivative of this guy with respect to x, then all that you get is e to the negative x cosine y. Do I get anything else when I differentiate this with respect to x? Is that the answer? Or? Yeah, so I'll stick it at the front. On this side, if you differentiate this fella, won't you get e to the negative y? If you differentiate a cosine, don't you get a negative sign? And those two negatives give you a plus. Are we comfortable about the plus and negatives that happened here and why they are? Okay, now we'll do the second one now. With respect to x, another negative cancels out the one that's already there, so that's what you get. When you do a sine and you differentiate it, you get a positive cosine. So we get that. And I'll put a bubble around that so I don't end up writing down the wrong thing. There's that guy. Okay, move on and do the y's now. With respect to y, won't you get e to the negative x? A cosine gives you a negative sine y. And this fella, well, e to the negative y gets you e to the negative y times the negative 1, so that's why this fella ends up being positive. Great. And then we'll do this double derivative. This guy gets you a negative e to the negative x cosine y. And this guy here gets you a negative e to the negative y cosine x. I'll put those two guys together. If I add this fella to this fella and this fella to this fella, is it pretty obvious that they actually cancel each other out and it's a solution? So your gut feeling was right. If you were looking at a function and you were trying to decide, is it a solution to Laplace's equation? There's a kind of structure that they tend to follow. don't they tend to have, if there's more than one term, that both terms will be very similar to each other, but the x's and y's swap places in some respect? And don't you also have to have some kind of negative thing going on? One's going to be plus and the other's going to be negative. So that kind of explains to me why x squared take away y squared works and why x squared plus y squared doesn't work. There are other features that I can tell you right now. If that was my u, will that solve a Laplace equation? Just gut feeling, looking at the structure of this u. Does that look like it's got the shape that a solution at least might have a fighting chance to work with?
No.
No. So Laplace aren't symmetric equations. That equation is not symmetric. I mean, if you switch the x's and y's, one of them's actually the negative of the other, right? So if a function doesn't have at least pseudo-symmetry, right? The two bits look the same, but they may have differences in signs, right? Then you're probably not, you could probably say it's not going to work without even doing it, and you'd be right. I'm about to leave this. This is us covered everything from the first section, partial differentiation. Anything you want me to talk about before I kind of close the book on this phase and move on to the next stuff? Okay. Let's look. Our next topic, darn it if I can remember what the number is, who cares? You can find out what the chapter number is. If I ever figure out, I'll put it there. But what it's about is important. It's called the chain rule.
It's 14.4.
Oh, thank you. So, chain rule. What questions use a chain rule? Well, let's keep it simple. If z is a function of, say, x and y, where x and y are themselves functions of another variable, let's call it t, then you will use the chain rule so then we use the chain rule to find the partial derivative of z with respect to t. So you know that you're on a chain rule question. If they tell you z is some function of x and y, and then they ask you not to find the partial derivative dz by dx or dz by dy, but they ask you to find the partial derivative dz by dt. So let's show you what that would look like. Let's suppose z is equal to x squared plus y squared, and that x is sine t, and that y is t cubed. Then if I wanted to find dz by dt, there is a formula called the chain rule formula that allows us to do this. And the formula is, oh, I should have put it here as well, dz by dx, dx by dt, plus dz by dy, dy by dt. Now, if you kind of look at this formula, this chain rule formula, can you imagine that you cancel out the x's? Do you see that what this piece here represents? Isn't it the contribution that x makes to the derivative dz by dt? And doesn't this one here, if you look at the y's essentially cancelling out, isn't this the contribution to dz by dt that the y variable does? So what you got here is a kind of you got to have caps on. So here goes. The partial derivative of z with respect to x is 2x, and dx by dt is cosine t. And the partial derivative of z with respect to y, in this case is 2y, and dy by dt is 3t squared. So far, so good. Now, I'm going to tell you something that I don't like, but we have to live with it. I'm going to do something here right now. I'm getting some feedback, so I'm just muting you all in case for some reason I missed one of you. Yeah, that's much better. Here, back to the question. This is the answer. Well, let's be a little bit more specific. This is the answer that you will type in to the homework. Strictly speaking, that shouldn't be the answer, algebraically. Does it make sense that if you're going to find the answer dz by dt, doesn't it kind of make sense that you should probably have your answer as nothing but t's? So I'm going to tell you what the answer should be if it was written down in a more proper format, just because I want to get this off my chest. But as far as you're concerned, in homework and in exams, if you write it like this, the computer's going to say you're right and we'll move on. So what I would be doing here is I would replace the 2x with 2 sine t, cosine t, and I'd replace the y by t cubed, so that's 6t cubed times t squared. I would then say that guy is the sine of 2t, and this guy is 6t to the 5. And as far as kind of the purest math people amongst us, doesn't that look like a much more useful version of the derivative? Because if you want to know what the partial derivative with respect of z with respect to t is, don't you really want to get the answer in terms of t? It kind of makes more sense. But you don't need to worry about that, because the homework WebAssign is quite happy if you just leave it as a mixture of x, y's and t's. As a chain,
sorry, will it mark us wrong if we actually did the substitutions and whittled it down?
that would be interesting. I don't know. Do it once. Do you know how you get 3 shots? On your first shot, take it to there. And if it likes it, that would be so much better. But if it doesn't, then just write the answer down. It's a piece of software. It's not the most intelligent piece of software. I've got a feeling that it just basically, the guys who write the questions put in a answer and it has to fit the answer, and it doesn't have an awful lot of flexibility in it. They may write down 3 or 4 flavors of that answer in case someone does a different flavor. It'd be really interesting to see if they did that. I would love it if they did. But what I'm saying is it's okay to do that, because you can only shoot with the gun that you've got, right? So if they only allow certain answers, we have to go with that. Are we comfortable about the process? How do you find using this thing called the chain rule? So far, so good. Right, let's up the ante a little bit. Let's have z equals xy squared plus 2x cubed, and x was t squared, and y was the natural log of t. And we'll get the partial derivative dz by dt. So the partial derivative of z with respect to x times x with t plus the partial derivative of z with respect to y dy by dt. Okay, partial derivative with respect to x. This guy here gets you y squared. This guy here gets you what? 6x squared. Partial derivative of x with respect to t just gets you another 2t. dz by dy now, the partial derivative, this guy gets you 2xy plus nothing. And this guy gets you 1 over t. There's really not much I could do to make this pretty. I'm not going to do really anything. And that would be the answer. So far, so good with chain rule. And it's really just adapting what you've already been doing, right? You've been doing tons of partial derivatives here. Do you see that all we do is we add in this little extra bit here and then try and make it look pretty, if it's possible. Okay, going to change, still on chain rule, I'm going to change it a little bit. Let's have a different variable w, who's x squared plus y cubed plus z to the 4. And let's suppose x is sine t, y is e to the t, and z 2t. And we're being asked to find that guy. So now we're going to have to adapt the chain rule formula. In this case here, do you notice that it's basically made up of 2 pieces? One for the x's and one for the y's. Can you see in this new world, aren't we going to have 3 pieces? So the adaptation to the formula is going to be the partial derivative of w with respect to x, dx by dt, partial derivative of w dy, dy by dt, and the partial derivative of w with respect to z, dz by dt. Does that seem natural? If nobody ever told you and you had to guess, is that probably what you would have guessed? That would be a good sign. So I'm just putting the details now. Question.
Mr. Robertson, I have a question. So as
Yeah,
you
score
can
race.
see, so delta W over delta X times delta X over delta T, don't the delta X cancel each other out? And then for delta Y, W over delta Y, and then delta W over delta Z, doesn't adding this create 3 times delta Y over delta T?
Oh, I see what you're getting at. Right. If you look at these, they look like it's fractions, and in fraction world, these cancel, agreed?
Yes.
But these are not really fractions. These are derivatives. They just have a notation that looks like fractions because of, you know, the slope equations and the solution to the tangent line problem. So they're not really allowed to cancel that and call it the w by dt. Although in a very loose way, I kind of sort of said that at the start, but I was trying to just say that in a kind of, this is the contribution to dw by dt that the x's give. This is the contribution that the y's give, and this is the contribution that the z's give. So you can't cancel them and just say that's going to get you 3 dw by dt's. It doesn't. It may look like that, but that's not really what's going on. So differentiate this with respect to x, you get that. Differentiate this with respect to t, you get that one. Differentiate this with respect to y, and dy by dt gets you this guy. And w gets you this piece, and dz by dw just gets you a 2. And if there's any tidying up to do, and there's hardly any, but there was a tiny bit, so I had to do it. that is the answer, at least as far as the WebAssign is concerned. Any other questions about what we've done up to this point? Okay.
Since we have 7 minutes left, do you want us to take attendance?
Yes, that's a good idea. Right, spend a minute, say hi to me. So I can spell Clairo. I actually wrote it down on a piece of paper. I think I've had, what, 3 versions of it so far, none of which were right. Okay, the 33 came through, which is somebody's missing. Okay, well, I guess I can find out who that is later. Right. So far, so good? Right, so let's expand it. There's not much more to expand, which is good news. Remember this version? If z is a function of x and y, where x and y are themselves functions of another variable t, then we can use the chain rule to find this fella, right? Then, what's the new version going to look like? Well, I'm going to use this as much as I can. If x and y are themselves function of another variables, typically called s and t, then we can use the chain rule to find dz by dt. Oh, it's the same formula. You see that? So what would that look like in practice? Well, suppose z was x squared plus y squared, right? Keep it simple. And suppose x was t squared plus s cubed. I have to do funny s's because my s's look like 5s if I don't. So that's what those funny little marks are about. And let's make y t e to the s. And let's suppose that we're being asked to find the partial derivative with respect to t, but now you can also be asked the partial derivative with respect to s. Doesn't that make sense? That either one of those two is a reasonable question to ask. Well, we'll start with the first one. I think the good news for my brain is it's the same formula, right? So you don't have to have a different formula because there's 2 variables. It's essentially the partial derivative of z with respect to x times this fella plus the y and that fella. Well, the first guy gets you 2x, and if you do a partial derivative with respect to t, well, what do you get? What's the partial derivative of x with respect to t here?
2t.
2t. Yeah, don't overthink it. It's just a partial derivative. It doesn't matter where it came from or that it's part of a bigger partial derivative. At that moment in time, isn't it just 2t? In that one instance. Now, if you do the y guy, you get this. Now, partial derivative of this guy with respect to t is e to the s. Have you noticed that in this question, the answer doesn't just contain x's and y's, which you kind of expect? Doesn't the answer also very often contain s and t, even although you're doing a partial derivative with respect to t, s's can still survive that process, can't they? Now, if I was taking it to the limits, I guess I would expect that you need to do that at least to get a correct in WebAssign. But if I was going to go full hog here, wouldn't I change this into that, and then try and tidy it up a little bit. How do you combine e to the s times another e to the s?
That'd be
No.
e to the 2s.
Correct. Not s squared, but 2s. So, in the grown-up math world, that would be considered a better form of the answer. In the WebAssign world, that guy is all they need. We cool with that? It annoys the heck out of me. I can't do anything about it. Maybe I'll buy WebAssign one day and fix it. But I'm going to have to win the lottery for that, so I don't think that's going to happen. Are we good? Right. We have got about we have got about 3 minutes left. So I'm just going to do a very, very quick version of the other one. dz by ds, right? That partial derivative. Right, as a formula goes, won't it be the partial derivative with respect to x? But now you do that guy. That makes sense. And the adaptation is quite minor. I think it's kind of intuitively obvious. Wouldn't that be the other guy? And like what Reese was saying earlier, these do not physically cancel, but in a kind of sort of a way, don't they cancel, in the sense that it shows you why this piece is a contribution that you get from the x's and why this piece gives you the contribution with the y's. Now, this guy is 2x. If you differentiate this guy, you get another 3s squared. This guy is 2y. And if you differentiate this guy with respect to s, you get this. And tidying up, you get this guy and this guy. Right, I'm looking at the two answers here. The boxes, my fingers are bouncing up and down on. I think we've already noticed this. There's no reason in the world, is there, that these two things should be the same. Right? We don't do this, and it would be nice if we had the time, I would do it. Couldn't I then take this answer and do a derivative with respect to t? And take this answer and do a derivative with respect to s? But if I was going to do that, shouldn't I do the full version? This version, right? And you should not be surprised that they're equal, because Clairaut's theorem doesn't care how deep the derivatives are of other derivatives, technically of other derivatives, until you get bored, right? As long as the functions that you're dealing with are continuous, the two partial derivatives with respect to the two variables will always be equal, which I think is I think it's probably telling us something really fundamental about multivariate functions, that they contain a structure that's very hard to kill.